Hello, I am Ahmed Nasruddin and I'll be presenting Deep Graph Sprints, our low latency representation learning method for continuous time dynamic graphs. This paper was developed at FIDSI together with my co-authors, and it was recently accepted in the Transactions on Machine Learning Research journal. Graphs serve as a foundational structure for modeling and analyzing interconnected systems with applications ranging from finance to healthcare, social media, and many others. Most real-world graphs are dynamic, meaning that they change over time, representing evolving systems. Dynamic graphs can be divided into two types: discrete time dynamic graphs, where the graph can be seen as a set of snapshots over time, or continuous time dynamic graphs, where the graph is continuously changing, with new edges or nodes being added or removed. In this work, we focus on continuous time dynamic graphs. In order to harness the relationship information encoded in the graph, one needs to extract this information into a lower dimensional embedding space. Existing techniques can be divided into graph feature engineering methods that rely on manually crafting heuristics to capture the graph characteristics, or deep learning-based graph representation learning methods that automate this process by learning compact embeddings of graph structures. Feature engineering approaches are time-consuming due to their manual nature. On the other hand, existing deep learning approaches might suffer from higher latencies, especially in inference time, making their deployment in real-time scenarios not possible. Therefore, trade-offs have to be made between manual work, latency, and performance, highlighting the need for our deep graph sprints, which is a low-latency, deep learning-based representation learning method. We will start by the intuition that led to the development of our method, namely random walks and graph sprints method. One naive approach to extract information from graphs is leveraging random walks. So since we are interested in temporal graphs, let's illustrate with an example. Given a temporal graphs where edges have timestamps associated and one target node A for which we want to generate an embedding, such an approach will start by doing the random walks starting from the target node A, say ABCD and AXY, and then while doing these walks, the engine could collect the features from the traversed nodes and edges, and after that, one can aggregate this collected information to generate an embedding or representation that represents the node A. Such an approach suffers from high latency due to the time needed to execute the walks and then summarize them. So instead of doing the random walks, in a previous paper, we proposed the graph sprints to approximate random walks in a way similar to moving average. Given an example graph, and since the graph is being built over time, unfolding one walk can be seen as a time series. So to illustrate the way graph sprints works with an example, given this example graph, and since it's being built over time, at timestamp 0, node D is initialized with a uniform embedding, and then at timestamp 2, the edge CD arrives, and to calculate an embedding for the node C, the previous embeddings of nodes C and D and the features of the arriving edge are used to calculate the embedding of the node C. Then at timestamp 4, the embedding of B is calculated only using the embedding of C and no need to look up older nodes in the walk, since C already contains information about D. So finally, at timestamp 5, the embedding of A is calculated using the embedding of B only and no need to go further in the walk, again, because the embedding of B already contains information about C, which contains information about D. So this is a very simplified example that shows the approximation of random walks and the reduction in complexity, as only the nodes involved in the current transactions are needed to obtain the embedding. Okay, so formally speaking, the current state of a certain node at timestamp t depends on its previous state and the previous state of its neighbor, and also on the features of the arriving edge, where alpha and beta are used as forgetting coefficients to control the weight between the past and present information and between the self and neighbor information. Moreover, the delta function is used to encode the input features. So as a result, graph sprints have several strengths like the low latency and the good performance. However, it suffers from a few limitations like the limited model expressivity caused by the scalar nature of the forgetting coefficients, and also the burdensome bucket definition in feature engineering stage for the delta function. And also another limitation is the decoupled optimization of the feature engineering phase and the component and the downstream classifier. So in this paper, we propose deep graph sprints, a deep learning approach that addresses the limitations of graph sprints while maintaining its advantages in low latency inference time. Starting from the graph sprints formula, one limitation of graph sprints is the uniform forgetting coefficients that could cause a limited model expressivity. So because it gives the same weight for all the features. So if for a certain feature we want to attend to more recent information, and for the other feature we want to attend to older information, we won't be able to do so. To address this, we transform the forgetting coefficients to vectors having one element per embedded feature, and also to avoid the tuning alpha and beta, we make them learnable, as we will see in a bit. The second limitation is having to define the edges of the buckets in the encoding function delta. To address this, we replace the delta function with a learnable embedding matrix W that maps the input features into an embedding space. This has several advantages. So in addition to removing the manual tuning process of the delta function, it also allows to control the embedding size easily. So, and in order to keep the characteristics of having the bins sum to 1 of graph sprints, we use a softmax function. In fact, we use several softmax functions, and to illustrate, so we use several softmax functions. Each one of these softmax functions is responsible for one part of the W matrix. This helps reducing the computational complexity of calculating the Jacobians during learning. And also, this technique has the potential to learn different information per softmax. Looking at the full architecture of deep graph sprints, it contains two components. The embedding component that leverages the formula that we have seen in the previous slides, takes as input the previous states and the input features, and also the forgetting coefficients and the embedding matrix to generate a state of our target node at timestamp t. This state is then input into a neural network component to generate a task-dependent output. So in order to address the manual tuning issue with graph sprints, the forgetting coefficients and the embedding matrix are learnable in a joint optimization way between the two components. And about the learning process, and due to the characteristics of our deep graph sprints method, namely that every pin in the forgetting coefficients corresponds to a single embedded feature, and due to the employment of several softmax functions, this reduces the computational complexity to calculate the Jacobians, therefore enabling the ability to perform forward mode automatic differentiation for the current component, and therefore being able to capture long-term dependencies. And as per the neural network component, we use typical backpropagation, resulting in the use of a mixed mode automatic differentiation. To evaluate our deep graph sprints method, we use the following experimental setup. As per the data, we use 5 different data sets from different domains. 2 of these data sets are internal to FeedZai. They are real-world data sets from the anti-money laundering domain. For these data sets, we cannot mention the exact details nor the identity of the financial institution due to confidentiality constraints. And the other data sets, they are external, publicly available data sets. All these data sets are labeled, like they have 2 classes each. And as per the number of edges, it ranges from around 150K edges to close to 2 million edges. As per the tasks, we use node classification task and the area under the ROC curve to measure and compare performance. Moreover, we use link prediction task, and to evaluate it, we use the mean reciprocal rank. Moreover, we compare our performance to state-of-the-art graph neural networks methods, namely TGN attention, TGN ID, and JODI. Looking into the results of the node classification task, here we show a trade-off between predictive power and runtime, where top left is the best since it means a higher predictive performance with a lower runtime or faster inference. Here we compare in yellow our deep graph sprints method with the graph sprints method, and the other colors are the other graph neural networks baselines. We notice that our deep graph sprints method achieves a competitive predictive performance while being faster than graph neural networks method. So here we show the gain in speed up compared to the TGN attention method. We see that it can be 5 times faster in Wikipedia and up to 12 times faster in Reddit. It's important to notice that the gain in speed increases with the increase in the number of edges in the graph, so we expect higher speedups with denser or larger graphs. Moreover, in the link prediction task, here we show the results from the transductive setting, meaning that nodes that appear in training can also appear in test, and we notice that deep graph sprints achieves a very good results. In fact, the best average rank across these 3 different data sets while being much faster than other baselines. To conclude, in this paper, we identified the limitations in current methods for continuous time dynamic graphs that typically have to do a trade-offs between performance and latency. And importantly, we introduced deep graph sprints method that enables real-time inference on continuous time dynamic graphs without compromising the learning of long-term dependencies. We also benchmarked deep graph sprints against other state-of-the-art methods and showed that it achieves a similar predictive performance while being up to 12 times faster. Thank you.